Hello everyone, I am Anvesh Gupta and in this video I am going to talk about several digital signal filters. This video mainly aims upon two filters like moving average filter and derivative filters. In this we are also going to see Arduino programs for the following. Now let's move on to see what moving average filter is. The moving average filter is a simple low-pass FIR filter which is commonly used for smoothing array of sample data. It takes L samples of the input at a time and takes the average of those to produce a single output point. As the length of the filter increases, the smoothness of the output increases, but the high frequency components of the data are made increasingly blunt. Now, uh, how this filter allows only the low frequency components to pass, we have to see the frequency response of the filter. But in order to see that, we have to first see the mathematical description of the filter. Now, the filter is mathematically described as y of n is equal to 1 upon L summation from k is equal to 0 to L minus 1 x of n minus k, where x of n is the signal which is sampled here. So now we take the z transform of the signal and calculate the transfer function. Now which is h of z, which equals to y of z by x of z. Now y of z is the output function and x of z is the input function, which equals to 1 upon 1 by L summation from k is equal to 0 to k L minus 1 z to the power minus k. Now let's see the frequency response of this filter. We see that this filter produces a cutoff frequency decrease when we increase the value of L. So we can see that when L is equal to 2, which is shown in the yellow lines, we see that the cutoff frequency is significantly high. So the high frequency signals are not suppressed to a great extent. But when we increase the L value to 8, we see that the cutoff frequency is reduced significantly and the high frequency portions are suppressed to a greater extent. When we keep on increasing this value of L, we see that the cutoff frequency is further reduced and the high frequency components are further suppressed. Now let's see the block diagram of this filter. We can see the block diagram of the filter, the x of n is taken as the input and this signal is delayed to as many times as we want in order to create uh, a moving average filter of the desired delay, and then all these are summed to give y of n, which is the output of the moving average filter. Now let us move to derivative filters. Now, derivative filter is a periodic bandpass FIR filter which is generally used in quantitative measurement of the rate of change of information present in a signal. We shall discuss two types of derivative filters here, which is the first order difference filter and the three point central difference filter. Now first let's see first order difference filter. The first order difference filter is a causal high pass LTI system which outputs the difference between the current and the previous value. This filter is used to emphasize high slope portions of the signals. Now the mathematical definition of the filter is y of n equals x of n minus x of n minus 1. The z transform the function of this can be written as h of z is equal to 1 minus z to the power minus 1. The frequency response of the signal shows that this is the high pass filter. We see that the low frequency components are suppressed and the high frequency components are allowed to pass with a significant gain. Now let's see the 3-point central difference filter. It is quite similar to the first order difference filter. The only difference is that it takes the difference of the current sample and the signal which is sampled two samples before it. So it can mathematically model as x of n minus x of n minus 2. Now the z domain transfer function is h of z equals 1 minus z to the power minus 2. Now let's see the frequency response of this filter. We see that the frequency response of this filter emphasizes that the gain is maximum near the frequency pi by 2, and the low frequency as well as the very high frequency components are suppressed. So we can say that this is a band pass filter which is centered around pi by 2. Now let's move forward. I am going to discuss the solutions to the experiment problems. The first problem is to choose a filter to smooth out high frequency noises present in the signal. The signal given us for this experiment is a PPG signal of 1000 samples. So in order to smooth this signal and remove the noises, I have used a moving average filter with L is equal to 8. Now let me walk through my code. So I have defined a float signal is a signal by SIG array of 1000 elements, and defined the values for this array. Now I defined the moving average filter with 1000 elements. Now I defined a sum which is going to which is going to be the intermediate value, which is going to store the intermediate value when calculating the moving average filter of the signal. Now the Arduino code is always having two parts, void setup and void loop. The void setup part runs at the starting of the Arduino board, and the void loop part runs for indefinitely. The void setup will only run one time. So now, like whenever so in order like first we have thing we do is we set the baud rate. So for that we have to write serial dot begin 9600. So I set the baud rate to 9600. You can change that to your desired value. So now we have to calculate the moving average filter. So for when I is less than 8, when the element number of elements which we are for which we are going to calculate the moving average filter is less than 8, we don't have that many numbers, a number of samples before it, since the signals are only defined for I is equal to 0. So what I did was I took the sample, like for the first sample I took the sample as the sample by 8. For the second sample I took the sample plus the previous sum by 8, and so on for the first 8 samples. Now from the 8th sample we have from the 8th sample we have a significant amount of sample for calculating our moving average filter. So the sum which was defined as the sum of the previous 8 samples plus the sum of the current sample by 8 minus the sum of the signal I minus 8 by 8. With this I minus 8 represents the sample which was 8 samples before the current signal. This has been done to improve the time efficiency of the algorithm. So now we assign this sum to the moving average value of I. So now we have calculated our moving average filter for the 1000 values of the signal. Now we are going to print it. So for printing it, we go to void loop part of the Arduino program, and in that we initialize loop from I is equal to 0 to 1000, and then we start printing our values. So we'll first print our signals to and then we print our moving average filter. So print the output of the moving average filter. Sorry. So for printing, we use serial.print command, and then we have to separate those two by a comma so that we can plot it using serial plotter, and then I printed serial.println. Now this println is used for is used whenever we want the next value to be printed to be printed on the next line. So now let's see the output of the moving average filter. Now as we can see that the blue represents the original signal, which consists of high frequency noises along with it. Now the red one is the the output of the moving average filter. We can see that the signal has been smoothed out. Now let's move on to the second question. The second question was to choose a filter to emphasize high slope portions in the signal. So for that, digital filters, derivative filters are used for emphasizing high slope portions of the given signal. As the given signal is observed to be PPG signal, we can highlight the local maxima of the same using the output of the derivative filter. Wherever the output of the derivative filter is at its maximum, there is the maximum. There is a maxima of the PPG signal. So here in this question, we are going to use both the derivative filter, the first order derivative filter and the 3-point central difference filter. For a better visualization of the output, we have smoothened out the PPG signal before passing it through the derivative filter. So in order to that, to do that, I have used this Arduino program. Now let me go to my program. So first I have initialized my signal as the 1000 values which were provided to us. So now the second thing I did was define the first order derivative filter, which is represented by FD, which consists of 999 values. Now, the 3-point central difference filter is denoted by CPD, which consists of an array of 998 elements. Now, for calculating the moving average filter, now again the sum has to be initialized to 0, and then moving average filter has to be defined with as an array of 1000 elements. So again, this program consists of two parts: void setup and void loop. So void setup, the first thing which I have to do is set the baud rate. Now then I have calculated the moving average filter using this from I is equal to 0 to I is equal to 8. So the same thing which I did in the last program. Then again, calculation of the moving average filter is still here. Now calculating of the first order derivative filter is done starting from here. So for that I have initialized a for loop which runs from I 0 to 999, and then the first order difference filter was defined as x of I is equal to x of I minus x of I minus 1. So I have taken moving average the output of the moving average filter at I plus 1 minus moving average filter at I. So this does the same thing as x of n minus x of n minus 1. Now again, moving on to this central difference filter, 3-point central difference filter. So in this, I have started a loop from I is equal to 2 to and the loop runs to I is equal to 1000, which so that I can pass through all the elements. So now this 3-point central difference filter is defined as x of n minus x of n minus 2. So that is what it is written in the code. Now let's print the values. So this printing of the value is done by this. So biases are added in order to visualize the functions properly. So the first thing which has been plotted in this is the moving average filters output of the signal, and then the first order difference output, and then the 3-point central difference output. Now let's see the output of the various filters. Now this the blue signal which we can see is the output of the moving average filter, which is the smoothed output of the original signal. Now the first order difference filter produces an output shown in the red. So we can see that this emphasizes in this we can see that the high values correspond to the high slopes of the PPG signal, and low values of the first order difference filter signifies the low slope portions of the moving average filter. Now let's move on to the green plotted line, which represents the 3-point central difference, the output of the 3-point central difference filter. We can see that this also signifies the same thing, but here we can see that the more intermediate frequencies are allowed to pass, and the lower as well as very high frequencies are suppressed. So this is the trend we can see here, like the low here the intermediate frequencies are allowed to pass, and the lower frequencies are not allowed to pass. So now let's move on to the next question, which is designing a moving average filter with L equals floor value of 0.8 into n, where n is the length of the sample signal, to extract the baseline drift component from the signal. So let me explain what baseline drift is. So whenever we record any signal, whether it be PPG signal or whatsoever, since we have used a PPG signal here, let's see what happens in it. So whenever we record a PPG signal, we get PPG signal plus noise plus the baseline drift. This baseline drift component is added due to the slow movement of the sensor, or due to the low frequency components of the surrounding. During the recording of the PPG signal, this low frequency component may be due to breathing and heart movement. So how to extract the baseline drift from it? Let's see. Firstly, we have to pass the given signal through a moving average filter, which removes the high frequency noise from the signal, and then we'll feed this output of this first moving average filter to another moving average filter, which has a L value greater than the L value of the first filter. The value of this L will be 800 to extract the baseline drift. As baseline drift is a very low frequency component, we need to we need to have this frequency component retained in the signal, but we have to remove the PPG signal from this. So finally, what we do in order to extract the corrected PPG signal is we subtract the output of the second filter from the output of the first filter. So let's see what is the coding for this. So first, this code is also similar to the previous code, which has two parts: void setup and void loop. So first we define the signal, then we define the variables which we are going to use here. Moving MAVH0 represents what we say is the second higher order moving average filter. This MAV1 represents the lower moving average filter. Sum stores the intermediate value of the higher moving average filter. S stores the BDE is the final extracted corrected PPG signal. L is 800, which is the value of and the size of the second moving average filter, and then there is S, which is the which is the variable which stores the intermediate value for the first moving average filter. So we'll begin code with void setup and define the baud rate at 9600. Then we go into the loop and write the smaller moving average filter. Then we go to the larger moving average filter here. Since we don't have the correct values of the moving average filter till I is equal to L, so what we do is, as before, we initialize the sum as sum plus moving average filter MAVI, which is the signal for the which is the input signal for the second moving average filter, and then we divide it by L. So what we get is the previous whatever previous samples are present, their value divided by it plus the current sample divided by it. Now we assign this to the ith value of the larger moving average filter. Now again, when I becomes L, we have sufficient we have got sufficient values of we have got sufficient samples in order to calculate our moving average filter. So we can write as sum. We will first determine this intermediate result, which is sum equals sum plus moving average MAVI by L minus MAVI minus 1 by L. This gives us the current value of the larger moving average filter, and then we assign this sum to the moving average value at I. Now what we have to do is extract the corrected PPG signal, which is stored in BDE variable. So now we do this. So we do this by assigning BDEI is equal to MAVI minus MAVH0I. So this MAVI consists of the PPG signal plus the baseline drift, and this MAVH0 is the baseline drift. So now BDEI consists of the corrected PPG signal. Now let's print it. So we go into void loop, then we start a loop from 800 to 1000 cents. We get the correct value of the larger moving average filter only after I is 800. So we start printing it. So we first print the signal, then we print the moving average filters output, then we print the baseline drifts moving average filters output, then we print the corrected PPG signal. Now let's see the output of the all the signals. So as we can see here in blue, we have the signal along with the noise. Now we pass this signal through a moving average filter, which removes the noise part, but it has the baseline drift component attached to it. Now the green shows the baseline drift of the signal, which is the value of output of the larger moving average filter, and the yellow part shows the corrected PPG signal. We can see here is that if we follow the 0 line here, and if we follow the minus 250 line here, we can see that when we remove the baseline drift, the PPG signal gets corrected and is almost like it's following a straight line. It's its values are oscillating about the straight line, but here we see that it ranges according it has an added baseline drift component. So now let's move on to the fourth question. So the fourth question was to find out the output of the signal processing system which performs the first order derivative filter and then performs the moving average filter with n equals 8. So in this experiment, what we have to do is first find the derivative of the signal, then smoothen it out using the moving average filter. Here I have used a moving average filter with n equals 8. So this gives us a smoothed derivative filter which has high values with where the slope of the signal is high. So in this also we have defined the signal first, then we have defined the first order derivative, then we have defined the moving average of this derivative, and then we have defined float sum d is equal to 0. This stores the intermediate value of this moving average derivative. It stores the intermediate value of this moving average filter, which is smoothing out the derivative filter. So let's begin with the code. So we set the baud rate equals 9000, then 96,000, then we perform the derivative filter here on the original signal, then we perform that moving average filter, which is the same as before. Then uh, for I is now when I is less than 8, then we don't have the correct value, so we pad it with some specific values. Then when we have I equals 8, then I from I equals 8 to 999, since the derivative filter can only be calculated for 999 values when the signal we have is of length 1000. So here we have the same thing. A little optimization has been done without the need of two loops. So sum d plus fd of I by 8 minus fd of I minus 8 by 8, and then we assign this to the moving average filter value, moving average filter output of the derivative function. So now print this value. So first we print the original signal, then we print the output of the of the derivative filter, and then we print the moving average output of this derivative filter. So let's see what happens. Now we see this that the signal is like this. Now when we take the derivative of the signal, which can be seen in this red, is that we cannot find out the high slope portion of the signal in this in this red signal, as there is quite a lot of noise involved in it. But when we take the average of this derivative filter, we find that the output is in green, and we find out that this has actually emphasized the high slope portions of the signal. We can also find that wherever there is the maxima of the PPG signal, we also find uh, in that region we see that the slope function has higher value. So with that, I would like to thank you for watching this video. Let's see you next.